Okay, here we go. Let's have a look. So we were talking on Friday, before our long weekend, we were talking about methods for evaluating limits analytically, right? And we said that, Jen, why don't you click that close? Everybody, phones away, focus up here. So we talked about the technique if I've got a rational function, so a ratio of polynomials, piece of cake. If you have an indeterminate form, then all you have to do is factor the top, factor the bottom, cancel the like factors, and simplify the function to evaluate the limit, right? So it's effectively filling in the hole, right? Give me thumbs on that. Is that ringing a bell? Remember that stuff? Okay. So what was our technique if something was a little more complicated? What if we had a limit of a complex fraction, you know, fractions divided by fractions? So we started to do this one. We said, okay, well, really all we need to do is just simplify this whole thing until it turns into a rational function, until we end up with something that looks like a polynomial divided by a polynomial. And our technique for doing that was we were going to get common denominators. We're going to combine these fractions through the use of common denominators, right? And we had started that process. We realized that the common denominator in the numerator is going to be the product of all the individual factors that show up in any of the denominators. And so that would be, what are all the different factors? Well, 10 and the quantity x plus 10. So we multiplied the first one by 10 over 10, second one by the quantity x plus 10 over x plus 10, right? And we got this, okay? Once we have a common denominator, we can push the fractions together and get that. Okay. If we distribute the negative and collect like terms, it starts to look simpler. The top fraction becomes quite a bit simpler. On the bottom, we've got x, which is the same as x over 1, and so now we've got big fraction on the top divided by big fraction on the bottom. Flip and multiply by the bottom, multiply by the reciprocal of the denominator, and that's where we had left off, was right here. Okay. So when we multiply fractions, we multiply straight across. So then we just get on the top negative x. On the bottom, we get 10 times the quantity x plus 10 times x. Let's just group the x with the monomial 10. So on the bottom, we get 10x times the quantity x plus 10 as x approaches 0. Now, if we try to evaluate this at 0, what happens? What happens? I don't just get 0 in the denominator. I get 0 both the top and the bottom, right? What does that mean? If I have 0 over 0, are we done? No. We're still in the process of doing the more work, aren't we? Because that's what we started off with, was we ended up with, if I tried to evaluate this, I got 1/10 minus 1/10, which is 0 in the top over 0 in the bottom, which means more work, which we're doing. But we're one step away. What's the last thing I have to do here to resolve that indeterminacy? Look how much better this looks now. I've got a ratio of, polynomial on the top divided by polynomial on the polynomial on the bottom is in factored form, but that's good, right? It's already factored for us. Without even looking at this stuff, if I have this written as polynomial over polynomial, oops, what happened there? Oh, I know what I have to do. Okay. I think, what the heck? There we go. Okay, without even knowing what the polynomials are on the top and the bottom, if this is indeterminate, if it's 0 over 0, you guys please tell me what factor is going to cancel in the top and the bottom to get rid of that indeterminacy so it's no longer 0 over 0. if I'm taking a limit as x approaches 0, and I get 0 over 0 when I evaluate that, what's the factor that has to cancel? Okay, let's review the factor theorem. If x minus c is a factor, what's the 0 that goes with that? X equals c, right? I can go either way with that. If I start off knowing that x equals c is a 0, then what's the factor that goes with it? X minus c. Okay, well, when we tried to evaluate this at x equals 0, we get 0 over 0, right? So x equals 0 is a problem. It's a 0 of the top and the bottom. So what's the factor of the top and the bottom that has to cancel then? X minus 0, which is just x, right? You get that? You already know what has to happen. You already know. You can anticipate before you even do any of this. That's what has to happen. Now let's make it happen. Oh, what do you know? What's going to cancel? X. Yeah. Look at that. Look how smart we were. Right? The x's canceled. And what did it leave me with? So then I just get the limit of what's left on the top if I cancel that x. Negative 1. What's left on the bottom? 10 times. Now I should be able to evaluate this thing and not have the 0 over 0 problem. What do I get? If I let x go to 0, what do I get? Yeah. Everybody agree? If I just let the x go to 0, yeah, I just get the answer. Negative 1 over 10 times 10. There's my answer. About that. Okay, good. So what moral of the story? What did we do? What was our grand strategy here? Just simplify the whole thing until it looks like a factored polynomial over a factored polynomial. You already know what factors are going to have to cancel, so cancel them and resolve the indeterminacy. Okay, the only thing is we made that more difficult than we needed to. What was the cumbersome part of this process? You got to think back a few days ago. But what part probably slowed us down the most? Yeah, finding the common denominator, combining the fractions, doing all that stuff, right? Is there a shortcut? You bet there's a shortcut. It's easier to just clear all the fractions by multiplying both the top and the bottom by the least common multiple of all the denominators, what the common denominator would be if we got it, okay? So what is that going to be? What's the least common multiple of all denominators in the top and bottom? 10. Well, okay, it looks like I've got, what are the factors that show up in the denominators of the top and the bottom? On the bottom, the denominator's 1. That's not a problem, right? But on the top, it looks like I've got factors x plus 10 and 10. So I'm just going to multiply top and bottom of this big fraction. I'm going to distribute through on the numerator and the denominator of this great big complex fraction 10 times the quantity x plus 10. Okay, so what's that look like then? So So what happens on the top when I distribute this whole thing to the first term? Anything cancel? X plus 10s. What do you know? Okay, so that gives me limit of 10, right? Everybody agree the x plus 10s cancel? Okay. Minus, when I distribute over here, let's get a different color, we're going to be brown, I guess. When I distribute over to there, to that term, what's going to cancel? 10. So I get minus the quantity x plus 10. Everybody agree? When I cleared those fractions. In the denominator, I'm just getting 10x times x plus 10 as x approaches 0. Does that look familiar? That's where we were in the previous process, clear down there. But wow, that was way more efficient, just clear fractions, wasn't it? Okay, so do that. Just distribute through. Again, the trick to skip all that cumbersome math is just clear the fractions in the numerator and the denominator by multiplying both through by the LCD of all denominators, top and bottom. In this case, the bottom was piece of cake though. Okay? Good? Make sense? Let's see if it makes sense. Go try one. This. So if we try to evaluate this directly, what do we get? 0 over 0, right? Okay, so then before we go any further, ultimately, what is the step that's going to happen that's going to give us an answer? What are we going to have to be able to cancel on the top and the bottom? X plus 4, right? We have to. We know that already because if we're substituting negative 4 for x, right? Really what we're doing is we're saying we're going to let x equal negative 4. If that's giving us 0 over 0, what's the factor that goes with that 0? X plus 4, right? So we already know. Now, I really want to know where you are in this. Give me a 1 to 5 on that concept. The concept of knowing that when all the dust settles, I know that what has to cancel is an x plus 4 because I'm approaching negative 4, and that's what's causing 0 over 0. Okay? So we can anticipate. Okay, that's good. I mean, the numbers will climb. But that's how we know eventually we have to be able to cancel an x plus 4. Now we just got to get there. We got to wade through the algebra to get to the point where we can do that cancellation. We already know it's going to happen, right? Okay, so what's the algebra? What am I going to distribute through on the top and the bottom? Okay, so first step. This is equal to the limit of 5 times the quantity x plus 9 times the original numerator, right? Divided by, I got to multiply the bottom by the same thing. And the reason I don't have to contribute anything from the denominator, from the fraction on the bottom, is that its denominator was 1, right? Okay, give me thumbs. Does that all make sense? Okay? So if I distribute, what's going to happen? So if I do the blue distribution, what's that give me? 5. Everybody agree? If I do the red distribution, what's it give me? What's it give me? The quantity x plus 9. Good, I need it in parentheses, don't I? Okay, on the bottom, I just get all that stuff. Okay, what do I need to cancel here? X plus 4. Well, I still don't have an x plus 4 on the top. What do I have to do? Simplify. Yeah, you got to distribute the negative and collect like terms. Okay, so that's going to give me on the top 5 minus x minus 9, which is the same thing as negative x minus 4. Not quite there. What do I have to do to get an x plus 4 on the top? Factor out a negative 1. There you go. Okay, so then we get limit of negative the quantity x plus 4 over 5 times the quantity x plus 9 times the quantity x plus 4 as x approaches negative 4. Now, finally, what cancels? And we're golden, right? We knew it had to happen. We just had to make it happen algebraically. So it cancels. And now I can take my limit. If I let x approach negative 4, what do I get on the top? I'm going to write one more step. Now, if I plug negative 4 and evaluate the limit, I get negative 1 over 25, right? Yeah. There's my answer. Good? Okay? All right. Okay, last one for today, I think. We'll see. Okay, what about limits involving radicals? Okay. Agreed, if I try to evaluate this directly, I get 0 over 0. Okay, this one looks a little tougher, right? Somehow I need to be able to cancel what factor in the top and the bottom? X. Agreed? Because if x is going to 0, doesn't that mean that we already know I need to be able to cancel x? X minus 0, which is x, top and bottom. The factor x needs to cancel. How in the world am I going to get that to happen? Okay. Any suggestions? Problem being, on the top I've got that radical. How in the world am I going to get an x out of the top? Okay, that's a good thought. If I square it though, I've changed the limit. I've changed the function, so my limit should change, right? I can't change the function, I can just change the way it looks. What are my options really? I mean, how do I do something to an expression and not change its value? I can either multiply by, what would I multiply by to leave something alone, not change its value? 1. Or I can add 0. We almost never add 0. 99% of the time we end up somehow multiplying by 1. Well, multiplying by 1 just means multiplying the top and the bottom by the same thing, doesn't it? What though? So I know I need to multiply both the top and the bottom by the same thing. The question is just, what would be a useful thing to multiply the top and the bottom by? It's going to be driven by the top, isn't it? The top is where we're having some issues. Yep. What do you mean by reciprocal? You don't mean reciprocal, you mean something else. Oh, okay. I see what you're saying. Very close. We're going to what do you think? Conjugate. Yeah. Isn't that the word you were looking for? We're going to multiply by the conjugate of the top. What's a conjugate? Let's remind ourselves what a conjugate is. A plus B and A minus B are conjugates. Okay? So then what would the conjugate of the expression on top be? Square root of x minus 1? X plus 1. Good. Square root of x plus 1? plus 1, exactly. Because this is like A, isn't it? This square root is like A, and 1 is like B. What we have on the top is something of the form A minus B. So we need to multiply it by something of the form A plus B, right? So we'll multiply it by square root of x plus 1 plus 1. And then the same thing on the bottom. Okay? Why is that so useful? Yeah, look what it did. When we multiply conjugates together, look what happens. If I multiply A plus B times A minus B, remember this pattern, this product pattern? What's that give you? No. You get A squared plus AB minus B squared, right? The cross terms cancel. I just get the difference of squares, A squared minus B squared. Right? That's useful because now look, on the top, that's going to give me A squared is just the square root of x plus 1 squared. What's that? X plus 1, right? Minus B squared is just 1 squared. That's 1, right? So I'm getting the limit of x plus 1 minus 1 on the top. On the bottom, I've got x times that big ugly conjugate. So you might be thinking, okay, well, great. What's the top simplify to? X. You might be thinking, okay, fine, Mr. Roy, but what did we end up with? Something that's just as ugly as what we started with, right? I've still got this big, ugly square root expression, this binomial expression with square roots in it. Why is this one way better than what we started with? Well, for one thing, we got the cancellation we needed. That's the most important thing, right? You guys told me before we even started this, I had to be able to cancel x's on the top and the bottom. We got them. What about this square root expression on the bottom? What's it equal to if I evaluate it? If I let x go to 0? 2. What was it before? 0. Huh. See? Kill two birds with one stone. It made things work for two reasons. The expression that's involving the square root is no longer going to 0, and we were able to cancel the x's. Make sense? Okay? So we cancel, what'd I do? So we cancel the x's, and we take our limit. I just get 1 on the top, square root of x plus 1 on the bottom as x goes to 0. Now I can take my limit and it's no longer indeterminate. What do I get? 1/2. Done. Okay? All right, so get rid of, for your notes, I'll just get rid of all that stuff. How about? Okay, that's called a rationalizing technique. Okay. Why is it a rationalizing technique? Because when we multiplied the top by its conjugate, we ended up with a rational expression, not an irrational expression. Now we don't have numbers stuck inside square roots. Okay? Get it? Okay? I believe you. Here's another example. Just for your notes, talking you through it. Okay, how that works. Put that up in the notes. You can read through it. It's in your textbook. Prove it to me. Actually, prove it to me. Go to the boards and try this. Let's make an important point here. What do you always try first? Direct substitution. Now I know you guys assumed, okay, we just did one like this, so he's getting it. But you always got to try it. You always got to try direct substitution first, and it works. This is a piece of cake. If I just evaluate this thing directly, I just get negative 12 over the square root of 16, which is negative 3, and I'm done, right? Okay? Okay, stay there. Try that one.